Now let's meet today's speakers. Slavomir Piatek, PhD, a senior university lecturer of physics at the New Jersey Institute of Technology. He is also a scientific consultant at Hamamatsu, where he has developed a photonics training program for engineers and is involved in popularizing silicon photomultipliers as a novel photodetector by writing and lecturing about the device. And we also have Mario Kasahara, a senior applications engineer at Hamamatsu, with a profound understanding of semiconductor technologies and specializing in MEMS mirror applications. He has more than 25 years of experience with the company's semiconductor products. And in his role at Hamamatsu, he combines his extensive knowledge with a passion for custom design detectors to deliver tailored solutions that meet diverse project needs. Thank you so much. It's so great to have you both here. I'm going to turn it over to you now.
So thank you very much for this nice introduction. And first, I would like to thank everyone for logging in to this Hamamatsu-sponsored webinar. As was stated, this webinar will be in two parts. The first part, given by me, Slavomir Piatek, will deal mostly with physics of MEMS mirrors. And the second part, given by Mario, will deal with technical aspects and some applications. So the index is as follows. First, we'll have a brief introduction, some technical background. Mario will then take over and discuss overview of scanning technologies. We'll discuss driving techniques and some more detailed application examples. So we know that there's an increasing number of applications where we use controllable mirror to manipulate light. For example, project light in desired direction. Such mirrors are examples of so-called micromechanical systems, or shortly MEMS. Please note that mirrors are just one example of such systems. A MEMS mirror, in principle, can move by translation, rotation, vibration, or some combination of these motions. And these motions can be achieved by various techniques of actuation. For example, electrostatic, piezoelectric, thermal, or electromagnetic. These mirrors have some very important characteristics like size, mass, rigidity, spring constant, reflectivity, and others. What you see at the bottom of this slide are examples of actual MEMS mirrors produced by Hamamatsu. First, some common examples where we can use MEMS mirrors. Here is an example of projector where we can feed RGB light into some beam controlling and combining system, which then illuminates mirror, scanning mirror, which then can project an image on some screen. Another common example of a MEMS mirror is a barcode reader, where again, by scanning the beam across the barcode, we can get information about the product or some other information encoded in the barcode. And the third common example of MEMS system is a 2D or two-dimensional optical switch, where light can go from one incoming fiber on the left to any desired outgoing fiber at the bottom. As we mentioned earlier, there are four ways of actuation, i.e. four ways of making mirrors move. One is electrostatic, piezoelectric, thermal, and electromagnetic. In what follows, I'll briefly discuss each one, but I should point out that mirrors produced by Hamamatsu are primarily driven by electromagnetic actuation. In case of electrostatic actuation, we rely on the phenomenon that if I have two plates, like in the capacitor, and I apply voltage between the plates, there will be a force. In the picture that you see, a spring here provides a restoring force. I can change separation between the plates by changing the voltage between them. In case of piezoelectric actuation, we rely on a phenomenon that certain crystals, piezoelectric crystals, will change their dimension. For example, in this case, thickness, by applying a voltage. In fact, there's a linear relationship between the two. This changing dimension will provide a mechanism for motion. In the thermal example, we rely on the fact that substances are going to either expand or contract when heated, i.e. when their temperature changes. In the final example, the electromagnetic actuation, again, the scope of this webinar, we rely on a torque produced by magnetic field and the magnetic torque which exists in the current loop. This relationship, or the torque, is proportional to the cross product between the two quantities. We're going to focus on this actuation a little bit more later, but at this point, I'd like to point out that the magnetic moment depends on the current that the loop carries and the area. In actual mirrors, the area is going to be fixed, the magnetic field is going to be fixed, it's the current that is going to change, thus turning the coil in a desired direction. Please note also the drawing torsional spring. So in MEMS mirrors, the coil does not rotate through 360 degrees. Instead, it's going to either change orientation or vibrate with certain frequency. The torsional spring is necessary to provide the restoring force. Therefore, because of the presence of the spring, this is a classic example of basically a driven harmonic oscillator. This is a summary slide of this section where we, in the top row, we have the mirror size. So there we see that MEMS mirrors will vary in size from about centimeter all the way down to about 1 micrometer in size. Below, we have examples of applications, and yet below, we have main actuation mechanisms. And from that, we see that two are the most common: electromagnetic, especially for larger mirrors, and electrostatic for smaller mirrors. Let's now look at the basic physics of mirrors. This background will help us in understanding how these mirrors operate in practice. So let's begin with the well-known law of reflection. If I have a mirror whose size d is much larger than the wavelength of light, an incoming ray is going to reflect in such a way that the incoming ray normal and outgoing ray are in the same plane, and the angle of incidence alpha is equal to angle of reflection beta. However, if I have a fixed direction from which light is coming, and I change the orientation of the mirror by angle theta, the outgoing beam is going to shift in direction by angle 2 theta. Thus, by changing orientation of the mirror, I can change direction in which outgoing light is coming. And so this provides or allows us one important application of MEMS mirrors, which is scanning or rastering with light a given scene. If the mirror size decreases and becomes comparable in some sense to the wavelength of light, diffraction will be more pronounced. So on the left-hand side at the bottom, you see an effect of diffraction, which means that the light, reflected light, is going to spread out. The amount of spreading will depend on the size of the mirror and also on the wavelength of light. And finally, if the mirror is not perfectly flat, if there are some bumps, grooves, irregularities, the reflected light will have a tendency to have some degree of diffuse. There will be some diffuse component. This is almost always undesirable in practical applications, since such light can provide unwanted photonic background. So we spoke about diffraction effect. So let's look at this a little bit more closely. As we said, the angle of diffraction delta theta is equal to ratio of the wavelength divided by d times a factor, geometrical factor g, which depends on the geometry of the mirror, whether it is circular or square or some other shape. As we said earlier, MEMS mirrors will be used for rastering the scene. Therefore, we would like to have some number of resolvable spots of light on the scene. Diffraction puts a limit on how many such spots you can have. So on the right-hand side at the bottom, you see an equation which gives me the number of resolvable spots given by theta max, which is the maximum angle by which the mirror can be turned, typically about 20 or so degrees from min to max for MEMS mirrors, divided by the angle of diffraction. Actual MEMS mirrors come in two basic varieties, i.e. 1D and 2D. On the left-hand side, you see an example of 1D mirror where there is only one axis around which vibration can take place. Remember, there's a torsional spring that makes the mirror vibrate, not rotate. On the right-hand side, you see an example of 2D mirror where there are two axes around which vibration can occur. So, as we said earlier, it is going to be electromagnetic force that will drive the mirrors manufactured by Hamamatsu. As we said earlier, the torque is proportional to the cross product between the magnetic moment and B. The magnetic moment depends, apart from the area, on the current. So where is the current? So there will be some wire either wrapped around the mirror or outside of the mirror, but it's going to be related or rigidly kind of in the same plane as the mirror. The current in this wire is going to be varied depending what type of motion you would like to extract from the mirror. Here is a top view of an actual design. If one looks more closely, it's hard to see. We see that the mirror is circular and the loops, the current loops are rectangular in shape. In what follows, we are going to now discuss some important parameters or characteristics of MEMS mirrors. And we'll begin with reflectivity. So at the top, we see a beam of light with certain power N being reflected from the mirror. Unfortunately, the power of reflection is going to be different, smaller than incident power. And that is due to a variety of losses, primarily absorption. Taking the ratio of reflected power to incident power, one obtains so-called reflectivity. At the bottom, you see typical reflectivity for MEMS mirror as a function of wavelength. We see that in visible light, we get around 90% peak reflectivity. Then there is a dip around 800 or so, and then reflectivity again recovers as we move into infrared. Reflectivity will depend on the type of material that is used for the reflecting surface. Another crucial characteristic is mirror flatness. As we said earlier, if the mirror is not perfectly flat, there will be some diffuse component to the reflection. Thus, here we have flatness, measurement of flatness as a function of position for the mirror shown on the right-hand side. And we see, looking at the scales, that the flatness deviates from some reference on the order of a few nanometers. The cartoon depiction, this is more realistic depiction of a MEMS mirror, namely it is enclosed in vacuum. The light that approaches the mirror has to pass through a window, a glass material. The picture shows us that the light will pass the window twice, on the way in towards the mirror and on the way out. The window will have an important effect on the light. First, there is a transmittance. So on left-hand side, we see light coming in, power in, and two phenomena occur. One is, unfortunately, reflection. So again, this reflected light can be a nuisance because can provide photonic unwanted background. And the rest light is going to pass through the window. However, looking closely at the picture, we see that power transmitted, or the beam transmitted, is offset with respect to power in. This offset is due to refraction. Taking the ratio of power transmitted to incident power, we have transmittance, which, as the diagram on the right-hand side shows, is a function of wavelength and also the angle of incidence. We see that the transmittance can approach for certain angles 100%, but typically it's below 100% and hovers in the high 90%. Here we see a more detailed view of what happens to light as it passes the window. So let's look again at incoming ray. We already learned that it's going to be displaced and strikes the mirror. The outgoing ray will go in the direction that depends on the angle theta. In this picture, we have three different values of theta. The outgoing light, as it passes through the window, will also be offset. But please note that the amount of offset, delta P, is unfortunately angle theta dependent. You may say, so what? Well, if I project this light on the screen and I have dots, the dots are going to be offset from the intended direction, and the amount of offset will depend on angle theta. This ultimately leads to distortions in the scanning pattern. Those distortions can be corrected to some extent, but if not corrected, they will be present. I should have pointed out on this slide that the delta P can be calculated from a geometry from basic optics. However, the equation that you see at the top is cumbersome to analyze. Thus, we made things a little bit simpler and made a plot of path deviation in millimeters as a function of optical deflection angle. And we see that for a given angle of incidence, the deflection, the amount of deflection will be some fraction of a millimeter. However, there is a linear relationship between that deflection and the deflection angle. If we go to different angle of incidence, the linear relationship persists, but the amount of deflection is different. One important property of a mirror is its size. And this is especially true if I want to have a focused light some large distance away, like, for example, in LiDAR. So here I have a source of light, laser, and I want the dot to have a dot some distance L away from the mirror. To do so, I have to use optical system lenses in such a way that the focusing occurs at the distance L after the reflection. That will require a certain size, minimum size on the mirror. And one can calculate this size, and it's given by equation in the top right corner. There we see that omega, which is the minimum size, is basically linearly proportional to L. So further out, I want to focus the light, larger the mirror needs be. You may say, so okay, so we get larger mirror. However, larger mirrors are going to have larger mass, and they also are going to be more prone to deformations, as we will discuss shortly. But first, there are two basic modes of operating MEMS mirror. One is the linear mode, or DC mode, where the location of the mirror, or the optical deflection, is a linear function of the drive current. So for example, if the drive current is minus 10 milliamps, the optical deflection is 10 degrees. If I don't change the current, the mirror stays at that location. Remember, there's a torsional spring that provides the restoring or the opposing torque. If I change the current to 0 milliamps, the optical deflection is 0, and so on. However, there is also a driven resonant mode. And before we look at it more closely, let's review some physics of resonance. So as we said earlier, a mirror attached to a torsional spring and driven by some current AC source is an example of driven harmonic oscillator. Every system has certain natural frequency of oscillations. Let's call it omega 0. On the right-hand side, you see a plot of optical deflection angle as a function of driving frequency. We see that for frequencies lower than natural frequency, there is basically a nearly linear relationship between deflection angle and the frequency. However, as the driving frequency approaches the natural frequency, the amplitude rapidly increases and reaches a maximum, the largest deflection at or near to the resonant frequency, or omega 0. So when we operate a mirror in that regime close to resonant frequencies, that is known as resonant operation. So on this slide, we see example of a raster scan where we have a 2D mirror such that in one axis, in this case, horizontal axis, we operate in the resonant mode, whereas in the vertical axis, we operate in a linear mode. And so, say, top line is produced, right? So we scan in X direction, then we change the current that controls the direction in Y, and we go to the next line, and so on. As we discussed earlier, because of refraction and also some other mechanism that Mario will discuss, we can have distortions in the scan. These distortions, as we expect, are going to depend on the angle of incidence, i.e., from which direction the laser light, whose direction we assume to be fixed, came from. And so in this example, 0 incidence gives us a better pattern than 20-degree incident direction. Again, one can correct, if one desires, to some extent, these distortions, and the corrections would involve changing in appropriate way. I know it's very vague, but it's also quite difficult, the current. Here is an example where we can scan the scene in so-called Lisieux scan. This would require that MEMS mirror operates in the resonant mode, both in X and Y directions. The actual pattern of scan will depend on the ratio of frequencies used in these two directions. So when a mirror vibrates, it deforms. And as we said earlier, the deformation will be size and material dependent. So here we have a plot for a vibrating mirror showing warpiness or deformation both in X and Y directions. We see that the amount of, excuse me, something happened. Suddenly the slides shifted. Okay, so we see that the amount of warpiness is on the order of micrometers, but again, that can be a lot in certain practical applications. I should also mention that when the mirror vibrates and the light reflects from such a vibrating mirror, there will be some degree of Doppler shift. And in many situations, that doesn't matter, but there are some applications like FMCW LiDAR where that Doppler shift could play some role. Now, we are probably wondering, how do I know in which direction the mirror is pointing? Do we know that direction? And the answer is yes. And the reason for that is a phenomenon known as back EMF. So again, back to physics. When conducting loop oscillates or rotates or moves in the presence of the magnetic field, a voltage or back EMF is going to be induced in that loop. On the right-hand side, we see a plot of a drive current, optical deflection angle, and back EMF. And we can see that there is a phase relationship, concrete phase relationship between the three quantities. So if you can tap into the back EMF, we can then determine the direction of or amount of optical deflection. Here is a very basic schematic of how we control the mirror and how we can determine its direction. So the input signal gets converted to current, and that current drives the MEMS mirror. However, the EMF produced is being tapped and then compared to the driving signal, and the difference is taken to determine the phase relationship. From that phase relationship, we can then deduce the direction. And Mario will discuss more in his section how this is actually done. Let's now discuss some temperature effects. So MEMS mirrors are likely to be used in situations where temperature will be changing. So what effect does it have on its operation? So first, here we see resonant frequency as a function of temperature. And we can see that there is a change, there is a decrease in the resonant frequency, all else being the same. You may say, oh, this is a very small change. However, remember, we are operating very close to resonant. And so even a small change in frequency has a dramatic impact on the deflection angle. Here we see the dependence of coil resistance with respect to temperature. Now there's a linear and rather dramatic dependence of the resistance. This is why we don't use voltage to drive the mirrors, because if that were the case, the change in resistance would produce change in current, and so that would not be appropriate. So current source, the amount of current passing through the coil will be independent of the coil resistance. Here we see the dependence of optical deflection angle on the temperature. So for the reasons above, there is a dependence, and what we see here is that the optical deflection angle is going to decline with the temperature. This is undesirable. However, there is a relatively straightforward way of correcting for temperature. There will be a thermistor inside of the MEMS mirror system, which measures effectively temperature. That information as a voltage is being passed to control unit, which will then adjust current in such a way as to remove the effect of changing temperature. So the operation can be stabilized against varying temperature. Another important effect is called ringing. Suppose I would like to change the orientation of the mirror from one angle, from one optical deflection to another. So we're going to change current in some manner, maybe a step manner. You can see from the middle picture that there is a ringing. In other words, it takes some time for the mirror to stabilize to the desired deflection angle, 15 degrees. So this exists in the linear mode, and we do have a mechanism to correct for that effect. So the next slide shows basically a sequence of what one does. And again, Mario will look into this issue more closely from the engineering point of view. In plot A, you have a desired input current. The shape is such that because we would like the mirror to be driven in this way. In plot B, the red shows the actual deflection of the mirror, and the wiggles show the ringing. In plot C, we have a Fourier transform. So we represent the input current in the frequency domain, and that's overlaid on the optical deflection curve as a function of frequency. The green mark shows the offending frequencies. These frequencies will contribute the most to the ringing phenomenon. And so what we would like to do, we'd like to change the time characteristic of the input power, the current, so that these frequencies are removed. So therefore, we perform inverse Fourier transform with those frequencies suppressed. And thus, in plot F, you have a modified input current, which would give you pretty much the same deflection of the mirror, but with suppressed ringing. How well we do is shown on this slide. So on the left-hand side, black is what we want, red is what we get, and green is the error. Please note that the error is expressed in percent, and so we see like one or so percent deviation between the two. After the correction on the right-hand side, again, there is some error, but please note the scale. The scale is now much smaller, and the error is much less than even 0.1%. And so with this slide, my part ends. I would like to hand over the presentation to Mario, who will discuss engineering aspects of MEMS mirrors and also some interesting applications.
Thank you very much, Slawomir, for explaining to us about physics behind the MEMS mirrors. And my name is Mario Kasahara, and I like to explain the engineering aspect of the MEMS mirror and also its applications. There are three sections in this presentation, my presentation. First, I like to go overview of the scanning technologies. And second, I like to address some of the electromagnetic mirror driving technique or some challenges you should expect using electromagnetic mirrors. And then finally, application examples. So this is first that I like to compare the overview of the three major scanning technologies. The first one is the galvan mirror. This is a really traditional, well-established scanners. And these are great advantage in the galvan mirror. It's established technology. Not only that, but you can get the larger mirror, and the mirror quality is very good. You can make a very discrete mirror. So that is a really good advantage of the galvan mirror. However, now the MEMS mirror comes into the market. Both electrostatic and electromagnetic has its own unique advantage too. The first probably advantage is the size, compact size. especially not only that the total package size is small, but also one unit can scan two-dimensionally, so that it makes really compact system possible. And also, another advantage is mirror itself is small. That's disadvantage, but smaller mirror can be moved faster way, so that when you need faster speed, frequency, or the frame rate, this MEMS mirror has its unique position in the market or the usage. I like to just talk about as a background what kind of mirror we're talking about here. I like to address that the electromagnetic mirrors that we make. Right now, 1D mirror and the 2D linear mirror both has a linear motion, and that the also 2D raster scan, which is a combination of resonant motion and a linear motion, is available right now in the market. What are some of the challenges and the technique you need to use the MEMS mirror? First, I like to start with raster scanning mirror. The raster scanning mirror's challenge is really locking into the resonant frequency of the mirror for the resonant axis. Why is it a challenge? Because the resonant frequency has a piece-to-piece variation and also temperature variation. So you need to have some kind of feedback loop to monitor and adjust the driving frequency. And the right side shows this is a block diagram of our driver circuit. This driver circuit has a feedback of that using the back EMF voltage, and then there's a way to stabilize the mirror movement. How do we do that? First, once again, there are two challenges: piece-to-piece variation of the resonant frequency and the temperature drift of that resonant frequency, and that is shown in the left side graph. As you can see, temperature shifts, resonant frequency drifts. It may look like small, but actually when you look at the optical angle by this resonant frequency shift, actually it's visible because the resonant frequency of the MEMS mirror is have a high Q factor. It's very sharp, so that the little bit of shifting of frequency turn into the large angle change. Then how can we avoid having such a instability? Right side, there's a block diagram. You can see the back EMF is tapped into the driver line. This is the line that goes to the coil driving. And that you tap into the back EMF from the coil of the mirror. And then what you're looking at is the phase of this back EMF signal. This back EMF signal has a symmetrical shape when it's moving in this resonant mode. However, when you start to go off of the resonant frequency, this symmetrical shape kind of shifts to the right or left. That becomes non-symmetrical shape. So that what you're looking at is a back EMF signal phase. You make the feedback circuitry. If it's shift to the right, there's a positive voltage, or shift to the left to the negative voltage. That kind of DC voltage is created and fed back to the FPGA that control the frequency of the MEMS mirror. In that way, you will always look into the mechanical resonant frequency of the MEMS mirror, thus that the angle gets stabilized. So that is a way to, some technique you need to stabilize the resonant movement of the raster scanning mirror. Next, I like to address the linear mirror challenges. Well, basically, linear mirror is very simple in its operation because the drive current corresponds to the tilt angle. It's very simple. However, when you try to use linear mirror in a very precise manner, there are some challenges. I like to address the three things. First thing is axis correction, and second thing is a ringing correction, and third thing is a temperature compensation. Let's start from axis correction. When this is unique to the electromagnetic MEMS mirror, and when you try to use an electromagnetic MEMS mirror, the one axis, outer coil x-axis, we call, x-axis moves according to what you expect. The drive current corresponds to the tilt angle. It's very simple. However, when you try to move the other axis, y-axis, which corresponds to the inner coil, actually the mirror moves diagonal to the y-axis instead of this perpendicular y-axis to the perpendicular y-axis. Why does this happen? The reason is written in below. First, that the inner coil has two-dimensional freedom of movement. Outer coil does not have only one three-dimensional movement of freedom, but inner coil can move in a y and x both axes. And then these 2D mirrors has a magnetic field applied diagonally. Thus, when you try to apply the inner coil, it moves diagonally. How can we solve this problem? Well, solution is adding the compensation current to the x-axis while you move the y-axis. Well, how do we do that? First, when you're moving the x-axis, it's very simple. The drive waveform converted into the current signal, and then you drive the x-axis, and it moves linearly according to the current. But when you actually add a y-axis movement, additionally to the regular y-axis driving current, you add the expected offset angle feed forward to the x-axis. This, based on this expected offset angle, you can recalculate the x-axis combined angle, original x-axis angle plus the y-axis offset angle. And then recalculate the altered drive current. And then when you drive that by the altered drive current, y-axis will be fixed to that the stable point. So once again, when you move the y-axis, you actually feed forward the expected offset angle to the x-axis, and by compensating that angle, that you can stabilize the y-axis movement. In that way, you will have perpendicular y-axis to the x-axis. Now, next, I'd like to talk about ringing correction. So Bomia mentioned about it, so that I like to make it very brief. Basically, when you have an intended waveform shown in the right side on top, it's a smooth waveform. This is the way you like to move the mirror. But actually, when you use this waveform, ringing rises on it. So how can we remove that ringing? First, you take the Fourier transform of this waveform, and in the frequency domain, in the center graph, in a frequency domain, you can subtract the resonant frequency of the mirror. And you take that inverse Fourier transform of this waveform, and you can create a modified waveform in a time domain. That is shown in the right side bottom. This modified waveform looks like there is a ringing itself, but actually when you move the mirror according to this waveform, actually you can get the very smooth intended waveform. This graph shows the result before the ringing correction there was a ringing writing onto the ideal waveform, and the error in green is large. However, after ringing correction, that you can see ideal waveform and actual waveform really coincide very well. And then error in green gets much smaller. So in this way, by using the Fourier transform and removing the ringing frequency in the frequency domain, you can correct the ringing movement. Final one is easy one, the temperature compensation. As this graph shows, the MEMS mirror has some optical angle has, or the tilt angle has, temperature dependency. When the temperature shifts, actually the angle also shifts. How can we compensate? Well, there is a temperature sensor built in the MEMS mirror. And by the temperature sensor reading, you can correct or compensate the drive current of the mirror. In that way, you can easily compensate the temperature drift. So in the next section, I'd like to explain the application examples. First one, many people know MEMS mirror for this application, LiDAR application. Why LiDAR? LiDAR uses the scanning laser spot, so that the MEMS mirror is used to scan this laser spot. And what kind of application MEMS mirror can be used? Right now, people are looking into the industrial automation or autonomous delivery, this kind of application. Relatively, in this kind of controlled environment, MEMS mirror works very well. For example, industrial automation in the factory, autonomous delivery, maybe in the company building facility or the hotel facility, that kind of well-controlled environment, this MEMS mirror will work very well. However, people looking into the autonomous driving on the street, yeah, that's possible, but more tests has to be done, more qualification need to be done, because the environment in the car can be very hazardous, and also accuracy of the reading has to be well tested before going on the street. But that is a possible future application. Another interesting application people are looking into is the smart city. Basically, your traffic monitoring and a security camera by LiDAR, and also smart farming, you're monitoring the crops growth. And why these things, LiDAR, can be used? Well, these things can be done by taking picture, but those things are dependent on the backlight conditions, like a daylight, night light, evening time, the background light is different. But however, when you use a LiDAR, you're always using the laser projecting to the object so that it's not dependent on the backlight conditions. So that in that kind of application, this MEMS mirror or LiDAR method can be used. Why MEMS mirror is drawing attention to this kind of application? The key is in this terminology people use in this field, mechanical LiDAR concept into quasi-solid state LiDAR concept. In other words, right now the many scanners are the pure mechanical scanners, but you can make that they remove or that they minimize the mechanical portion of it by using the solid state like a MEMS mirror technology. Then why that the quasi-solid state solution is better? Well, you can expect a higher reliability. Well, mechanical things prone to break, so that minimal moving components result in the minimum breakage, so that the reliability you can expect to be heightened by moving from the mechanical solution into non-mechanical solution. Well, the MEMS mirror has a mechanical factor in it, but in the industry, it is considered as a non-mechanical solution. Another advantage of using MEMS mirror is a system size reduction. Yes, that the 2D capability with a one unit, and then the unit itself is much smaller than the mechanical scanners, so that you can expect the reducing the size, total size of the scanners. Another advantage of the MEMS mirror is increased frame rate or increased speed. Right now, that the mechanical mirror, you can make a bigger mirror, but MEMS mirror, you can make the mirror smaller, thus you can make the movement faster. That can be an advantage. Right now, our raster scanning mirror has a high resonance frequency of 30 kilohertz, and that can result in the higher frame rate. This is just a resonance frequency is 30 kilohertz, so that it's just one axis that the frequency, but that can make the whole frame rate faster. Especially this is important when you are trying to capture the moving objects, such as automobile or some other machinery around. So for the moving object, this increased resonance frequency or increased frame rate is very attractive. Now, what are some of the key requirements for the MEMS mirror? The first thing is high reflectivity. Especially this type of light application, you are aiming for the long distance. And right now, with a gold coating in a near-infrared range, 95% or more is possible. And another key spec is a large mirror area. In Slavomia's presentation, resolution was explained. This resolution of n, number of resolvable spots, is proportional to the d, which is diameter of refraction, which is limited by the MEMS mirror diameter. So when the diameter of the MEMS mirror is larger, you have more resolvable spots. So resolution gets higher. So that is why the large mirror area is important. Another factor is a distance too. In the previous physics section, the distance L was related to the omega, which is a beam radius on the mirror. It's not linear relationship, but the larger the radius of the mirror, omega, the longer the distance L. So that if you like to get the longer distance, also the large area of the mirror is required. Another thing is a large angle, which is understandable because you like to have a wide field of view. And also that you may have noticed the resolution formula above, there's a theta max there. That is the angle of the mirror. Is also related to the resolution. So that for the resolution also, large angle is desirable. And also high resonance frequency is very desirable because if you try to capture the moving object, you like to have a higher frame rate. Right now, MEMS mirror, horizontal direction 30 kilohertz, but self-driving car, which I think use the mechanical mirror, only has a 0.5 to 2 kilohertz, so that you can expect a higher speed by using the MEMS mirror. Next application I like to mention is OCT, optical coherence tomography. What is optical coherence tomography? I like to explain the principle by this spectral domain type. Basically, it is an interferometer with a broadband light source. And that the backscatter broadband light source will be split into the two arms of light. One is a reference mirror, is fixed, and then another light goes into the sample and scanned by the MEMS mirror. So MEMS mirror is used in this as a scanning device here. And that the backscatter from the sample come back to the beam splitter and combined with the reference arm light, and thus cause the interference. And by checking each wavelength interference, you can get the depth information of the sample. Basically, the interference pattern has a wavelength dependency, so that by using this scheme and analyzing each spectral line, you can obtain the depth image of the sample. There's another type of OCT, which is a swept source OCT. In this scheme, you use the wavelength swept light source instead of broadband light source, so that each time the wavelength is swept in a different wavelength, and then you can use a single detector, single bandwidth detector. And usually, as a detector, a balanced detector is used for the high signal-to-noise detection. And another big difference between the SD and SS OCT is the wavelength range they use is usually different. Spectral domain, they use like 840 nanometer range, but swept source, they like to go a little bit deeper into the tissue so that they use a longer wavelength, so that 1060, 1300 nanometer laser is usually used. Then why MEMS mirror is used for this application? Well, the makers are thinking about home doctor or self-care use. Right now, the OCT is a big instrument in that specialist's office, but they can make the compact and the low-cost machine that can be placed in the home doctor office. And in the future, also it might be possible to have the patient's house for the self-care use. In this way, you can screen some of the risk you may have in the eyes, and then when you have that risk, the home doctor can send for the specialist for the more detailed checkup. In that way, MEMS mirror can be used in a compact, low-cost OCT machine. What are the key specs required for this application? First thing is a mirror size. Why? Once again, the resolution N is related to the D, diameter of the refraction. So mirror size has to be relatively large. Another thing, mirror flatness has to be there. The above resolution formula is only applicable when the mirror is flat. If the deformation of the mirror, either static or the dynamic, is larger than 1/10 of the wavelength, that now the mirror deformation dominates they limit the resolution. So the deformation has to be 1/10 of the wavelength, at least 1/10 of the wavelength. Another thing required is high speed. Since that the OCT often look at the eyes, and eye is constantly moving. So for high resolution image, you like to scan the image as fast as possible. So the high speed is another important factor. Well, right now that the available electromagnetic mirror is relatively small, 1.2 millimeter, but this is a future developmental things that we are developing, 2 millimeter mirror and a 5 millimeter mirror. And that according to the mirror size, optical deflection angle and the frequency has to be adjusted, but that these large mirrors are possible. And also the material can be changed from aluminum into gold mirror. In that way, you can achieve the 95% of reflectivity in the over 800 nanometer region. So thank you very much for your attention. And we'd like to pass on this to the moderator, Justine.
Great. Thank you so much. That was fantastic. And now let's move over into the Q&A. As I mentioned earlier, if you'd like to submit a question, just type it into that Ask a Question box and hit send, and we'll answer as many as we can before time runs out. And we do have some in here already, so let's get started. Is the wavelength shift due to angle the AR coding on the MEMS window and not the MEMS mirror coding?
Oh, I'm sorry. Can you repeat the question? I'm sorry.
That's okay. Is the wavelength shift due to the angle to the AR coding on the MEMS window and not the MEMS mirror coding?
Oh. I'm sorry, I'm not sure, but I think it should. But I don't know the degree, how much the shift will happen. So about that one, I have to really probably get the data for you.
Okay. And are Hamamatsu MEMS mirrors available in production volume?
Yes, it is available. Now that all those 3 mirrors we introduced are available in production volume now.
Okay, great. And it looks like we are just about out of time, unfortunately. And any of these questions that we did not get to today will be addressed directly with our speakers later. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Slavomir Piatek and Mario Kasahara for an excellent presentation, Hamamatsu for sponsoring today's webcast, and of course all of you too for joining us. Enjoy the rest of the day.